Now, we have just a few more minutes to deal with this part of very fundamental nuclear physics, and it's somewhat descriptive. I will try to point out the things that you really need to remember. If we take a look here, the average annual radiation in the United States to which the average person is exposed, you see, in millirems per year. Now, these are not rems, but thousandths of a rem, millirems per year. You have cosmic rays, 28, natural body radiation. Your own body is radioactive, and it exposes itself to that radioactivity. And you see the number of millirems per year you pick up is 28, etc., etc. You see other information. Note nuclear reactors, very, very low. And a total of somewhere in the vicinity of 157 millirems per year. Whereas that's the annual radiation, the dose that we receive, in other words, we can be exposed to a certain amount of radiation, but the actual dose, what strikes the body, either internally or externally, is about 360 millirems per year, as you see here, 360 thousandths of a rem per year. And now these are things I'm going to point out that you need to remember. Consumer products produce or give us a dose of about 3% of all of that radiation, just 3% from consumer products. Note that number. Radon, 55% of all the radiation that we receive is due to radon. You'll need to remember that number as well. And then you see medicine is 4%, cosmic and terrestrial, 8%, medical x-rays, 11%, internal, 11%. And I would remember certainly the point about the consumer products and the fact that radon is more than half. And I would also remember that internal radiation is 11%, contributes to 11%. Now, we'll spend just one or two visuals on how the damage occurs in the body. And the radiation effects are due primarily to ionization. Now, what the heck is ionization? Well, if you have an atom and an alpha particle sweeps by the atom, maybe it misses it, but it gets close by, it can remove one of those outer electrons. That's called ionization, and that damages the atom. Another technique would be, another form of ionization, if you like, is if you have a molecule which consists of an array of atoms, a half a dozen atoms bound together. If an alpha particle strikes that molecule and breaks it in half, then you've obviously damaged that molecule. If it happens to be, for example, a DNA molecule, then you have the potential for genetic defects. So what you see here on this visual, damage from ionization, direct radiation is what I've just described, damage done to cells by the breaking of the chemical bonds of biological molecules to include DNA. Now that's direct radiation. There is indirect damage as well, or that's direct damage, not direct radiation, direct damage. There's also indirect damage that you can get. And what happens here is an alpha particle comes in, say, is passing through your body at some point and hits a water molecule, H2O. 70% of the body is a water molecule, is made up of water, and so a lot of the damage will be to water molecules. So the alpha particle comes in, strikes a water molecule, breaks it in half, and the water molecule, because it's broken in half, now has a net charge on it. In other words, the water molecule is typically neutral, but if you break it, you can't be assured that you get half the positive charges on one side and half the negative on the other side. Typically, that isn't what happens. And so these pieces of water molecule are charged. And as they move around in the body, because they're charged now, they can interact with the body in ways that are not normal. And that when they do damage, when those pieces of the water molecule do damage to the body, that's called indirect damage. In other words, the alpha particle actually damaged the water molecule, which then damaged other parts of the human body. And that's indirect damage, and you see it here. That's damage done by the creation of chemical radicals. Now, a chemical radical is nothing more than those pieces of water molecules from water in the cell which attack the biological molecules chemically. So that would be indirect damage. Now, some of the effects that you can see, some of the symptoms, if you like, due to ionization damage. I've delineated here, you have the swelling of cells, they get a little bigger. The viscosity, the fluid in the cells increases, it becomes a little thicker. The permeability of the cell walls increase, the cell walls allow more fluid to pass in and out of them. And of course there's some interference with cell division. So the upshot to all this is on the general considerations for health effects. What kinds of things would I like you to remember out of this is these here. That you have a dose from a high exposure for a short time or a low exposure for a long time is really about the same. That is to say that if you're in a high radon concentration but only for a couple of minutes, that is as much a health risk as if you were in a low concentration for a prolonged period. Also, just two other terms, if the effects appear immediately or very, very soon, we call them acute, and if it takes a long time for the effects to occur, they're delayed, and typically that is a cancer that is being formed. And the delay time for radon is generally seen to be on the vicinity of 15 to 20 years. That is, if you're exposed to a high radon concentration and you didn't know it, for 15 or 20 years, you'd see the cancer in that 20th year or so. It takes that long for the effect to occur, to show itself up. Now, how do we know that there is a health risk due to radon? I want to talk about that for a minute because it's going to introduce a couple of terms, again, we need to be familiar with. And we know what the effects of high doses of radiation are. We have data from when the U.S. bombed Hiroshima and Nagasaki, and we know how many people died in those cases due to the high doses of radiation. We know what the doses were, we know how many died. When individuals used to paint the lines on watches that glowed in the dark, if you remember that far back, the watches used to glow in the dark. They had a little bit of radium, actually, radium-226, right on the watch dial, on the hands of the watch. And so you could see those hands even at night because they were glowing. They were radioactive, of course. And how do you make a real fine line? Of course, you lick the brush, and then you deposit the paint, the radium paint, right onto the hand of the watch. And these individuals who had done this, of course, got cancers in their lips and tongues, and there are photos of these things. In other words, we know what high-dose radiation does in producing cancers. We know that effect actually quite well. But we don't know what happens to the potential for cancer if the radiation is small. We actually don't know that. If we take a look at this chart, here I've drawn on the vertical axis cancer rates and on the horizontal axis the exposure, that is how much radiation we're exposed to. And in the high concentration areas, where there were very high concentration, we know what the health effects are. In other words, we know that, and I don't know what the numbers are exactly, but suppose we know that if you're exposed to 10,000 units of radiation and you expose 1,000 people to that amount of radiation, so you get 1,000 people exposed to 10,000 units of radiation, suppose you get 100 people who come down with a cancer. If you cut that exposure down in half, we know that the number of people who come down with lung cancer also decreases by a factor of a half. That is, as you continue to decrease the exposure, you decrease the number of cancers produced by that exposure, and it's linear. You cut it down by a half, the number of cancers, the number of diseases due to that radiation also goes down by that very same factor. Now, what we don't know is if the exposure is very small, does that same linear relationship hold up? Down here, you see, I've indicated by the straight line that as you decrease the exposure, you're also decreasing the cancer rate. Now, at the very low exposures, I've drawn it in with dashed lines to indicate that we don't have much data here. With good reason. It's very difficult to keep track of very low exposures for very long periods. Longitudinal studies of this type are extremely difficult to do, and you'd have to do them over 20 or 30 years. So that kind of data is simply not accessible to us at this moment. Now, it is quite possible that if you look at the straight line relationship between high exposures and cancer rates, it is quite possible and quite reasonable to assume that that straight line continues on right through to the origin, indicating no exposure, no cancer rates, at least due to radiation. And that is the current accepted philosophy, that we assume that there is a straight line relationship even at the very low concentrations, and that there is no concentration below which there is no health risk. That is, regardless of how small the concentration, we think that there is some health risk associated with that. And that is called the linear, that is straight line, linear no threshold hypothesis, the linear no threshold guess. It is possible, of course, that something else could be occurring. And perhaps someday when the data becomes available, we'll find out which one of these curves is correct. It's possible that the straight line could curve down, as I've indicated here, and stop at some point, which I've chosen to call the threshold. And this would indicate, if this were true, that the concentrations below whatever this value is at the threshold produce no cancers. That is, there is a threshold. That's possible. And that would be called a threshold hypothesis. That is, that there is some point below which those exposures do not produce any cancers or any radiation diseases. There are other assumptions, as you can see in the graph. It could be that instead of following a straight line, it could follow a curved path. And you can make almost any guess you want. It could follow a curved path and then drop down with a threshold or no threshold. Hard to say. The current belief among most scientists in working in this arena, we do accept the thought that straight line, no threshold, is certainly the most prudent assumption to make, and it is the one which guides most of our activities in radon now. So you need to remember, straight line, no threshold is the hypothesis currently assumed in the health physics area. Again, there's an array of questions which follow this, and this ends actually part 1 of very fundamental nuclear physics. I'd like you to deal with the questions that follow, check your answers in the back of the book, and then return for part 2. In part 2 of the program, we're going to discuss the issue of radon in water. And first, let me point out to you how the radon gets into the water and why it is, in fact, a health risk. A lot of the water that we drink, a lot of our potable water, of course, comes from underground, not solely reservoirs. And the radon is generated underground. That radon, if there's water near it, will percolate into the water as well. And then when you take the water into the house, the radon comes out of the water. So for example, you go into the shower stall, you turn on the shower, and as the water comes down and strikes you, the radon is going to be allowed to escape. You can then inhale those high radon concentrations. You'll see they're quite high. You can inhale those radon concentrations, and that's where the health risk begins again. So it's not that radon in water is a health risk. It's that radon in air is the health risk, but the radon in water can become the radon in air. And in fact, it typically does. If there's radon in the water, believe me, there will be radon in the air where that water is used. Now, there's been a very large number of studies, very conclusive data is in place regarding the radon in water issue. And here, I've chosen to look at just a few states, Pennsylvania, Maine, and New Jersey, and look at some of the high values of radon in water. 103,000. These are all picocuries per liter of water. 41,000, 92,000, and low values on the order of 100. Let me just point out that the low values of 100 are actually not the low values that are found, but the instrumentation that is used to measure radon in water typically has a little bit of difficulty getting values below 100. That is, the concentration is so low that the instrument has a hard time picking it out. And so typically what you're looking at here is the lowest level of detection, much more than actually the lowest value of radon in water. But note that the values are on the order of 10,000, 50,000, and 100,000. In fact, one house in Maine had a radon in water concentration on the order of 1 million picocuries per liter. Now, those are typical values that you can expect to find in radon and water measurements. You don't find in radon and water measurements 5 picocuries per liter, 10 or 50 picocuries per liter. Typically, you see them in the hundreds and in the thousands for radon concentrations. In water, that is different from what you see in air. If you saw 100,000 picocuries per liter in air, you'd be some concerned about that. But that is not quite as significant a concern for radon and water. I have here tabulated some further typical values taken out of another article. Trailer park was found with about 4,000, campground around 3,000, private home 8,000, service station 5,000. Just to place into your mind that the radon and water concentrations tend to be in the orders of hundreds and in thousands of picocuries per liter. As I point out to you, the reason it becomes a health risk is that it becomes radon in air. The reason it's not a health risk if it stays in the water is, remember, the radon decays into the daughter products, and the 3 dangerous daughters, the 2 poloniums and bismuth, and the daughter products emit these alpha particles. But if all of that's occurring in the water, then those alpha particles, which have a very short range, never escape out of the water. And so you could drink it, let it pass through your whole system, and the alpha particles would never touch your body parts because they would be in the water that's being flushed out of the system, so to speak. So the hazard is that the radon in water becomes radon in air. At least that's the currently accepted hazard. And I've here picked out some values for how much is released. Again, another article. If you use this is a closed washer cycle, 98% of the radon is released in that cycle. Whatever radon there was in the water, that's all in the air now, or just about all. Cold wash cycle, 93%, etc., etc. Now, what I would like you to gather out of this is, although not all these numbers are 100%, fundamentally, the more you disturb the water, the more the radon's going to escape. Makes sense, easy to remember. If you disturb it enough, you can get just about all of the radon to escape. And fundamentally, that's what I want you to remember, that all of the radon in the water tends to become radon in air. That's not exactly true, but nevertheless, if you remember that, that will give you proper guidance. Now, how much radon in water becomes radon in air depends, of course, on how much water you use, how you use the water, and if you're a typical family in a typical house using typical amounts of water, the relationship between the radon in water and radon in air concentration is typically taken as 10,000 to 1. And what I mean by that is that for 10,000 picocuries per liter of radon in water in an average home, that will induce 1 picocurie per liter of radon in air. So if you had 40,000 picocuries per liter of radon in water, you should expect that in the house, that will produce 4 picocuries per liter of radon in air. So 40,000 would give you 4 picocuries per liter. 10,000 picocuries per liter of radon in water would give you 1 picocurie per liter of radon in air. Now, much of this you will get only from wells. If a house takes its water from a well, then you're much more likely to get radon in the house due to the radon in water than if you're on city water or a public water supply. And the reason is this: if you're using a well, and the well's right there next to the house usually, when you take a shower and you use maybe 30-40 gallons of water in the shower, then you're obviously taking well water directly into the house. And there's radon in the water, and so that's coming into the house. But if you're on city water, and you have and perhaps it's based on a reservoir, then first of all, the reservoir is constantly being disturbed by the air blowing over it, etc., and the radon is escaping out of the reservoir, even if it's in the water. Which means that as you take water from the reservoir, and it may take, I don't know how long, it may take hours or days for the water to go from the reservoir to your house, in that case, the radon has an opportunity, whatever radon is left, to decay even further. And so typically, well water will produce radon and air problems, and reservoir water or city water is not nearly as expected to produce a radon and air problem. So that's mostly due to wells. Now, I show here a sketch of what the radon and air concentration looks like for a home that has a radon and water problem. And what you see here, I've plotted on the vertical axis the radon concentration in picocuries per liter, and again on the horizontal axis time. So this would be in hours, and perhaps the entire time from the origin out to the edge here would be 1 or 2 days. And if you have a radon and water problem, and you're measuring the radon continuously, here you see a continuous radon monitor would be very useful. Whenever you take a shower, in this particular case, a couple of showers are taken, the radon concentration goes up and then drops off to a low level. Then the dishwasher in a shower is used, goes up, comes down to a low level. Showers used, goes up, comes down to a low level. The very lowest level is the problem due to radon in the soil, probably, but the peaks are due, of course, to the radon in water. And so if you had a continuous radon monitor, you could get this kind of hourly printout, for example, and see whether or not the radon problem is radon in air or radon in water. So this particular graph shows that in this home, the radon problem is a radon in water problem. I think you can see as the days go by that we will want to be able to test for radon in water just as regularly, at least for houses with wells, as we test for radon in air. This next graph that I've drawn, again, drawn very much the same way. Vertical axis is the radon concentration, and that would be in picocuries per liter, and then time along this axis. And I've indicated baths, laundries, and showers. And note here that the baseline is at 5 picocuries per liter, roughly, and that when you use water, of course, you have a radon and water problem showing up. But it never drops much below 5. So in this particular one, this graph would represent a home where the home has a radon and air problem and a radon and water problem as well. If you had no radon and water, when you use the laundries or take a shower, you would not expect to see high radon concentrations follow, as you see here. In this third graph, note the vertical axis starts, the lowest value I've indicated is 50, and then 100 picocuries per liter, and O for opening a window, C for closing a window, and S for a shower. And notice that a shower does tend to produce a little bit of a peak in the radon concentration, although not significantly, and the base below all of these values is up around 100 picocuries per liter. This house predominantly has a radon and air problem, and the radon's getting into that particular house from the soil issue. Now, the way the radon will be mitigated in homes, there are actually two techniques, but fundamentally I believe the way it'll turn out in homes is that the radon will be mitigated at the point of entry. That is, if you have a well and the water comes in through your basement or comes into the house somewhere, that's called, where that pipe first enters the house, the point of entry of the water. And typically the solution will be, to mitigate the problem, is we put a fairly large charcoal tank, stands 4 or 5 feet tall, of activated charcoal, and the water will pass through that charcoal on its way into the house. And the charcoal will absorb the radon out of the water, along with numerous other things, and then the water going into the house will be relatively radon-free. That's fundamentally how it will be treated. A second method is, as you see here, a second method is by the process of aeration. And I don't think this is going to catch on for homes, but in the area of aeration, what's done is the water would be taken up from the well, and it would be allowed to enter a container that perhaps would have a paddle going through it, splashing the water around. And then above that, the air would be evacuated. It would be vacuumed out continuously and deposited presumably into the outside atmosphere. The water would then be repressurized and put back into the house. Now, that's a technique that would work for large water systems, but in principle would be relatively uneconomical for homes. The mitigation for radon in water, then, I would like you to recognize is that it will be done, or it should be done, at the point of entry. And for homes, activated charcoal will be used, and for larger facilities, aeration will be the process. I do have a visual here which shows an activated charcoal tank, and here's the well water coming in this way. There's usually a pre-filter to pull off whatever sediment there is to get it out of the water so it doesn't pollute the GAC tank, the water would come down through the tank and then up through the tank, guided by the appropriate piping, and then up into the household. And this tank would then accumulate the radon. Of course, we have to pay attention then. The tank itself has the potential for becoming a radioactive waste problem, but that can be dealt with and without much difficulty, something we'll deal with at a later time. Now, I would like to show you how to take a radon and water sample, because that's important, and it is covered on the exam. Fundamentally, the thing I would like you to remember about taking a water sample in a house is you go to a faucet generally as close to the well as possible. You turn the faucet on, and you let it run for a few minutes so that the water that's coming out of the faucet is well water, not water that's been in the holding tank for 2 or 3 days, but well water itself. So you leave the faucet on for a few minutes. You want to disturb the water as little as possible while you take the sample. Bearing in mind, if you splash the water around, you're going to lose a lot of the radon, and your measurement's going to be a crummy measurement. So as you watch the part that's coming up, watch for those kinds of things, that the water's not being disturbed, that if there's an aerator on the faucet, that it is being removed, and how carefully the sample is prepared. Now, we have gone to another laboratory for this portion of the video, and they will show us how to take a radon and water sample. So if we could go over to that laboratory portion and then return to the video at this point. Hi, Ken.
Hi.
Nice to meet you.
Nice to meet you.
Richard says you can take the water sample for us.
Sure,
so
we'll show you exactly how it's done.
Okay, great.
Basically what we start out with, we'll start out with the kit itself. You'll receive it like this. It comes with a SEPTA cap and vial and an instruction sheet, meaning all the instructions are on the back part of the sheet, and the information that we'll ask you to fill out's on the front. The way you start out taking the sample, you want to remove any kind of aerator from the faucet itself.
Now, the aerators, they always unscrew?
Right. They always,
yeah.
most of the time they unscrew, unless someone puts on, let's say, a Teledyne type water filtration unit that's on the outside of the sink. Then you have to do some finagling there, but it's basically you're just unscrewing something, and any homeowner can do that.
Okay.
You want to turn the water on and get it running. You want to take some kind of container, relatively large container. We have a 1 gallon pitcher here. That works out fine, and allow it to fill up completely. And you want it to allow the water to start overflowing.
And I see you keep the water, the faucet, submerged.
Right.
Is that useful?
Right. And basically what you're trying to do is you're trying to not create any kind of disturbance from the water coming out of the tap into the container itself.
Well, that's because any agitation will tend to eliminate the radon.
Right. It's going to aerate into the air, and you'll have actually a contamination problem right here while you're breathing and taking the sample. Right.
And more importantly, the sample will not represent an accurate radon and water measurement for your home. Right.
Correct.
Right.
So we'll allow this to run for approximately 1 or 2 minutes, and then once we're basically done allowing it to run, we can set this down very carefully, turn the water off. You want to take the vial, take the cap itself, and the thing that's really key here is to make sure, this is a SEPTA, make sure that the SEPTA is placed correctly inside the cap and screwed on correctly. The way the side that you want to have down against the glass would be the red Teflon side, and the soft, subtle side you want to have out towards the air. So what we'll do is we'll take this vial, we'll slowly place it below the water line. We'll take the cap and the SEPTA down inside together. We'll put this whole thing together underneath the water line, making sure that there aren't any bubbles trapped inside the glass vial.
Okay.
And sometimes it's a little tricky. You need to agitate a little bit sometimes, but it comes out. Now, if there's a real small bubble inside, don't worry about that.
Okay.
But we'll take it out. You can dry it off. Place it inside the box.
Okay.
And then we're going to ask you to fill out the information sheet that goes with it. The most key and most important thing on this particular information sheet, if you don't even fill out your name and address, it should get back to you. The key thing that's going to have to happen, though, is you have to remember, number 1, the serial number that was on the vial itself. Okay. And number 2, you have to make sure that you fill in the sampling date and time that you took the sample. That's key to getting a correct and accurate result.
Sure, because if it makes 2 weeks ago that you took the sample, there may not be any radon showing up.
Right.
Whereas there might have been some radon in it 2 weeks ago.
Right.
Right, okay.
So we'll just ask you to fill that information out. Then once you fill it out, and we'll just put in today's date. And the time would be 9 a.m.
Now, suppose there are several sinks in the house. Is there one sink that we should take the water sample out of as opposed to another sink?
Well, the best place to take the water sample would be closest to the source of the water. So if you have a tap that's, let's say, in the basement right next to the wellhead, that's the ideal place to take the sample.
What if there's, between the well and the tap that you're using, suppose there's a water softener or something like that?
Yeah, you try to get it before any kind of treatments happen to it, so that you know what's happening with the water in the house. What could possibly happen while it's being treated, there could be some agitation of the water and you're releasing radon. You really don't know what the number is before that agitation. You'll know what it is after, if you take the sample after.
So actually what you're looking for is the radon and water measurement in the well. You'd like to get it in the well, and taking it out of the faucet is an easy place to get it. You want to take it out of the faucet that's closest to the well.
Sure.
Without any agitation prior to that. Okay. Now, how long should it take to do this test? If I'm a typical homeowner, I've never seen this test kit before. It shows up, I open the box, and I say, oh God, now I've got to do this test. How long? How many minutes should it take me to do it, roughly?
Well, like I was saying before, it should take 1 or 2 minutes to allow the water to fill up the container itself. You would like to hear the well pump kick in if you can.
Sure. You want to get all the water out of the lines in case it's been sitting there for a few hours and having some decay in the process.
Sure. So, I think the maximum amount of time you're looking at is about 10 minutes.
Okay. To do the whole thing?
To do the whole process.
So you probably let the water run 4, 5, 6 minutes as a reasonable amount of time.
Sure.
Fill the vial. That didn't look too tricky.
No.
Make sure the red part of the septum faces the water. Faces the glass. Screw it on tight. Check to make sure there's no air in it, no significant amount of air, and put it back in a box. Fill out the form correctly. Fold the box, put the postage on it, and get it back in the mail. And that's it. I hope you saw the things I was asking you to look for, and in any case, we're going to see how much of all of this you remember. There's a set of questions that follow this point on the video, and I'd like you to deal with those questions as usual. And this ends part 2. So do the questions, look at the answers, make sure you understand the answers, then return to this part of the video and we'll move along into part 3. This is part 3 of the review program, and in this part we're going to discuss the Citizen's Guide to Radon. Now, this is what the homeowner would get if they call the appropriate state or federal agency in order to get some information about radon. Typically, they'll get a few pamphlets. This will be one of them, and also a list of people who are certified or that the state or the federal agency believes that somehow they have some ability to do radon measurements and radon mitigation. In any case, the homeowner typically gets a small pack of materials, and this is one of the items in that pack. Beyond that, this is one of the 7 items that is covered on the EPA RMP exam, which is why we're covering it now. And just as in the previous parts that you've seen, and in the parts yet to be seen, I have extracted the most salient points that you may be tested upon in the exam. So let's follow along now with the Citizen's Guide to Radon. As you can see in this particular visual, the EPA makes a set of recommendations to the homeowner. First, that they should test, that it's easy to test. And we know, of course, that it is easy to test. And the second item is that if the concentration comes out to be 4 or more picocuries per liter, that the homeowner will be recommended to consider fixing the home to get the concentration down. They also say, as you can see in item number 3, they also point out that the concentrations less than 4 picocuries per liter still pose a health risk. The EPA says that if you're 4 or more, and we've heard this before and we'll hear it again, if it's 4 or more, the house should be mitigated. In the past, in the very beginning of the radon issue, the EPA did not say what to do if it was less than 4. But now they're saying that even if it's less than 4, that there is still some health risk. So at least they're committing to that. And we've seen in the earlier issue that this fits in with the straight line, no threshold hypothesis of radioactivity's impact on our human health. The EPA goes on to recommend to take a short-term test, as you see listed here as item 4A, to take a short-term test. And for our purposes, a short-term test is anything between 2 days and 90 days. And in 4B listed, if the concentration is again 4 or more, to take a follow-up test. Now this fits in 4A, this fits in with the idea of a screening measurement, which was the old format that used to be used, and then with a follow-up measurement afterwards. The idea being that if you make a screening measurement, that is your first test, that in that measurement you have taken and gotten a value perhaps of say 6 or 7 picocuries per liter, and that is a short-term measurement. It is not an annual average. And the action limit of 4 picocuries per liter is an action limit over a year's average. What I'm trying to say here is that the EPA action limit of 4 picocuries per liter is assuming that you're living in a home or that a home exists where on the average over the year the concentration is 4 picocuries per liter. The recommendation is to fix it. The recommendation is not if you make a 10-minute measurement and you get a value greater than 4, you should fix the house. Now, how can you get close to a full year average if you're taking short-term measurements? Well, the idea is, well, you first take a screening measurement of on the order of a few days, and then you take another second measurement. Then typically if the average of the two is greater than 4, that's a good indicator of the annual average. Now, in this particular graphic, we see that in item number 5, the follow-up measurement is to be a short-term measurement or a long-term measurement. Again, remember, short-term is 2 to 90 days, and a long-term is more than 90 days. And they tell you that if the concentration from the screening measurement is more than 10 or equal to 10 picocuries per liter, that the follow-up measurement should be a short-term measurement. And if the concentration is less than 10, then you can do a long-term measurement to get a better annual average. Now that makes sense, and I want to explain to you the sense of these things, because then it's easier to remember if you understand why these things were developed. And in this case, if the concentration is greater than 10, suppose it's 50. Well, do you want to spend 3 or 4 months waiting to find out if it really is 50 and put yourself in that particular hazard for that extra period of time? The answer, of course, is no. And so if it's greater, if the screening measurement is greater than 10, the recommendation to the homeowner is to do a second measurement short term. If the screening measurement is less than 10, then the recommendation is to do a long-term measurement. Now also, as you see in item number 7, if the long-term measurement is 4 or more, or if the average of the 2 short-term measurements is 4 or more, then the recommendation is to fix the home. Actually, the terminology is they recommend that you should consider fixing the home. But fundamentally, the idea is under these conditions, you should fix the home. They further recommend to the homeowner, and this is a newer topic coming into play, that if the air concentration is 4 or more, that the well should be tested. Obviously, this is true only for people who are on wells. If you're on city water supply, then of course this doesn't make any sense. But if you have a well and the air concentration is found to be greater than 4, then the recommendation is you should test the well. And the item number 9, they recommend that you fix your home before you try to sell it. Now we know that the majority of radon tests that occur are in homes where there's a sales agreement in play or the house is about to be sold. And obviously it's easier to sell a house if there are no problems with the house right off the bat. And so the recommendation here, fix your home before you sell it, is a good idea. It avoids a lot of problems. Now, the EPA goes on to make a bunch of statements, and you need to be familiar with these statements in regards to the exam. One is that lung cancer deaths due to radon are approximately 14,000, and that's 14,000 per year. That's a reasonably large number. They further go on to say now they're going to talk about where to put the detectors and under what conditions should these detectors be placed. Again, I'd like you to remember that this is the information that's being presented to the homeowner. The recommendation is to place detectors in the lowest lived-in area. Now, that is different from what it had been in previous years where it was the lowest livable space. Now it is in the lowest lived-in area. So if you're looking at a home that's, say, a colonial home with a basement, 2 stories with a basement, but the basement is hardly ever used for anything, then the lowest lived-in area would be the first floor, not the basement. Of course, if the basement has a rec room in it and it's used frequently, then the basement becomes the lowest lived-in area. But note the difference from previous year's protocols. The further closed house conditions should be maintained if the test is going to be between 2 and 3 days, or 2-3 days, short-term measurements, very short-term. The closed house conditions should be met for 12 hours prior to the beginning of the measurement, and you may want to jot that down at this point, 12 hours prior to the beginning of the measurement, and during the measurement as well. Now, closed house means, of course, we want to minimize the outside air that's being brought into the building. So if you have a window fan, that should be stopped. If you have an air conditioner, say a window air conditioner that's bringing outside air in, that should be reset so that it does not bring outside air in. So that's what we mean by closed house conditions. No attic fans, no whole house fans, those kinds of things that can greatly change the value of the radon concentration in a house. It can abuse the value to the point where the short-term measurement doesn't even come close to the annual average. So we want to minimize that, and so closed house conditions for 12 hours prior to the measurement and during the measurement. Do not test in bad weather. The reason for not testing in bad weather is generally bad weather comes about with a low pressure, low atmospheric pressure. If there's a low atmospheric pressure, it's simply that much easier for the radon to percolate up into the house. The difference can be an order of magnitude. If, for example, if you knew that a year-long radon concentration was 2 or 3 picocuries per liter, but you make a measurement during inclement weather when the atmospheric pressure is low, that number could come out to be 20 or 30, 10 times as much, just because of the weather conditions, which detracts from the correlation between the short-term measurement and the long-term value. So do not test in bad weather. Make the test in a frequently used room. The idea being that why test in a room where we hardly ever spend any time at all? Let's test in rooms where the health hazard exists. That is where the humans spend time. So we want to test in frequently used rooms. Do not test in kitchens or baths. The reason for this is many of the detectors, especially the charcoal canister detector, can be impacted by the amount of moisture that exists in a given room. And kitchens and baths typically have quite a bit of moisture in them. Secondly, there's typically more ventilation in a kitchen and in a bathroom than there is in the rest of the house, and that can impact the value of the radon concentration there as well. So typically not kitchens or baths. The test measurement should be made by a detector deployed at least 20 inches above the floor. And you see here I have it listed as more than or equal to 20 inches above the floor. So that's the minimum height requirement where we will deploy these detectors, 20 inches above the floor. Purpose for that is keep it away from drafts that exist along the floor. We're not entirely certain of the impact of drafts on how some of these detectors work. And so because we're uncertain, let's keep them away from drafts. So let's keep them off the floor by 20 inches or more. You also note directly under this, keep it away from drafts. We just talked about that. High temperatures and high humidities. And the reason that we have these constraints in, that high temperatures and high humidities can have an effect on several of the different detector types. So we want to keep them away from that. And we want to keep it away from outside walls, the reason being that outside walls often have ghost drafts along the surface of the wall. EPA continues to tell the homeowner that the average indoor level is 1.3, and that is probably a reasonable average in the United States. The average outdoor level is 0.4. Now note this, noting that the average outdoor level is 0.4 means that it will be close to impossible to lower the radon concentration in a home to less than 0.4. It could be done, but it would require superhuman efforts to have that happen. Here in this studio at East Stroudsburg University, I have brought a detector And I'm going to turn this on, and you'll be able to listen to the background. It takes a minute for this to warm up, but I think you can hear the beeping. And in this studio, there is some radiation in the room. And what you're listening to is what we call background radiation. It is, for all intensive purposes, impossible to eliminate background radiation. As we saw in an earlier segment, even the human body is radioactive to some degree. And part of that is being registered by this particular instrument. Now, going back to this visual, we see that if two short-term tests, just look at this statement for a second, if two short-term tests yield an average of 4.1, you have a 50-50 chance that the radon concentration is less than 4. Now, I'm not suggesting to mean that the two short-term measurements had error in them. What I'm pointing out here is that you have a 50-50 chance that the annual average, and you may want to jot that in, the annual average will be less than 4. So if you're making a measurement and it's very close to 4, that is, say, just over 4, 4.1, then you have roughly a 50-50 chance that the annual concentration will still be less than 4. Well, that's what they're told. And I believe that is quite true. Now, what follows on the next page is an array of questions that I would like you to answer just as you have in the past sections. Hopefully you found that you got all the questions right, and if not, you found all the right answers after you tried the questions. One other comment I want to make that is not in the visuals, and I would like you to write this down, perhaps on the page you're looking at right now, and that is that the EPA also points out to the homeowners that they expect that 1 out of every 15 homes will have a radon problem. 1 out of every 15. And you should be familiar with that number for purposes of this exam. Now, the next issue is on what are called false positives and false negatives. This is actually not in the Citizen's Guide, but it's a good place to put this particular topic. And the definition of a false positive, as you see here, deals with a measurement. And if you take a measurement, a false positive indicates, I'm just going to read this, the value determined is on the positive side of the action limit when the actual value is below the action limit. And I give an example. Suppose that you're going to a radon chamber, and the chamber concentration is set to 2. And I'm going to be talking about picocuries per liter here. So the chamber concentration is set to 2. But you go in, you deploy your detector, whatever detector type you're using, you deploy your detector, and you make a measurement, and it comes out to be 5. Now, that's a false positive. It's false because it's on the wrong side of the action limit. That is, the actual value is on the low side. But the value that you found by your detector, for whatever reason, is on the high side of the action limit. It's on the positive side. So it's false because it's on the wrong side of the action limit. It's positive because it's on the high side of the action limit. So it's a false positive. Whereas, if you take a look at what a false negative is, defined and very similarly, a false negative indicates the value determined is on the negative side of the action limit when the actual value is above the action limit. So again, let's go to a radon chamber where we know the concentration is, say, 5, and we put our detector in there, and after the prescribed amount of time we take the detector out, and we find that our detector tells us that the concentration is 3. Again, it's false because we're on the wrong side of the action limit, and it's negative. We're on the low side, whereas the chamber is actually on the high side of the action limit. So that would be a false negative. And let's think about this one now. This one's not in writing, and I just want you to think about it. Suppose that you have a radon chamber, and we set the concentration in the chamber to 2. You deploy your detector in there, and after a prescribed amount of time, you remove it, and your detector tells you that the concentration is 3. To review that, we have a radon chamber set to 2. Your detector tells you the chamber is 3. Is that a false positive or a false negative? And the answer is, it's neither. It's not false because it is on the correct side of the action limit. That is correct in agreement with the actual value in the chamber. It is below 4. It's somewhat inaccurate, but at least it's not a false positive nor a false negative. Okay? And there will be questions that follow a little later on that will give you some chance to exercise your understanding of this false positive and false negative. Let's go back to what the EPA recommends now in the Citizen's Guide, and the recommendation is to retest if the living patterns change. Now that makes good sense, and we should bear this in mind, that if you start using your basement, for example, suppose you install a rec room where before you weren't using the basement hardly at all, then you should retest in that space. They further tell the homeowner that in mitigation processes that a reasonably good mitigation system will typically lower radon concentrations to less than 2. And you need to remember all of these things. I'm not delineating any of this material because it seems of completeness, but primarily to review for this exam. And so please make careful note of this information. The EPA continues to give out more information. In particular, it specifies roughly what it has experienced as mitigation costs. And what we see here is that the range of mitigations run between $500 and $2,500, with an average value of $1,200. And they go on to say in the Citizen's Guide that these kinds of costs are typical of the kinds of costs to make other home repairs. For example, if you have an oil furnace and the oil furnace fails and you have to replace it, you're going to spend money in these ranges between $500 and $2,500 to get these kinds of repairs done. So the EPA tells the homeowner that the cost of a mitigation system is very similar to the costs of other kinds of home repairs of this magnitude. They also tell the homeowner to retest periodically every 2 years. Now I think this is a good idea. If you're on a well, typically you test your well every few years to make sure that the condition of the well is still in good condition. And here the recommendation is to retest periodically every 2 years. So if you're familiar with homeowners who have had their houses tested or you've done the house testing, then you might want to generate a reminder file or a tickler file which 2 years from now you look at the file and it says, oh yeah, today I should call Tom Jones and remind him. Maybe you could send him a little postcard saying your test was done 2 years ago. EPA recommendation is that you should test again, and this card is to remind you of that. So retest periodically every 2 years is an EPA recommendation. Now, also in the Citizen's Guide, there's a table of health risks for smokers and non-smokers as a function of radon concentration. And there's a lot of data there, and when I first looked at it, I thought to myself, gee, how can anybody remember all this data? But I did find, if you'll bear with me, a relatively easy way to pick out the data, and all you have to do is remember one or two things. Now, the first thing I want you to note is under non-smokers, right here, you see if the concentration is 2, that the non-smoker has a chance of 1 out of 1,000 for achieving a lung cancer. And what that means is if you live a lifetime in a concentration of 2 picocuries per liter and you're a non-smoker, that the odds of you getting a lung cancer are 1 out of 1,000. Now look further down in this chart. At 4 picocuries per liter, the non-smoker has a risk of 2 out of 1,000. Now what I want you to note here is this. The risk for a non-smoker is half the value of the concentration. If the concentration is 2, non-smoker has a risk of 1 out of 1,000. If it's 4, it's 2 out of 1,000. Now you're going to think I'm misleading you because I'm sure you've all looked at 8 already and seen that that's not 4 out of 1,000, it's 3 out of 1,000. 10 gives you 4 out of 1,000, 20 gives you 8 out of 1,000. But the easy way to remember this, I think, is that the concentration, the health risk rather, is half the concentration, but as you get higher and higher, it's just a little bit less than half. And that will give you a close enough value to be able to answer the questions on the RMP exam. Now it stands to reason that this should be the case, that as the concentration gets higher, the health risk does not get linearly higher as well. That is, it gets higher, but it drops off a little bit. The reason being that if the health risk at 2 picocuries per liter is 1 out of 1,000, suppose I make the concentration 2,000 picocuries per liter. Should that make it 1,000 out of 1,000? Exactly 1,000 times the concentration would give you 1,000 times the risk, which would guarantee that everybody gets a lung cancer. And yet we know that humans don't react that way. There are some who still will never get a lung cancer. And so you can't just continue to increase the concentration and say that the health risk increases linearly as well. Although that is typically the supposition we make, it is not exactly correct when we get into the very high concentrations. And that effect you see here. 2 gives you 1, 4 gives you 2, 8 doesn't quite give you 4, it gives you 3. 10 gives you 4, 20 gives you 8. If you went to 200 picocuries per liter, your guess might be, well, it's going to be under 100, and maybe 80, 85 would be right. And so I think you can remember all of these, at least for non-smokers, simply by recognizing that the risk is roughly half the concentration. And as you get to higher concentrations, it's a little less than half. Now that's for non-smokers. Now let's look at smokers. I have a method for this too. For smokers, note the risk is 15 out of 1,000 at 2. That's 15 times the health risk of the non-smoker. Now the reason it's so much more is that when the radon decays, the daughter products are solids, and they tend to adhere to the dust particles in the air, the smoke particles in the air. And if you're a smoker, you're inhaling those smoke particles, they're adhering to your lungs, and so what they're actually doing is they're fastening the radioactivity right to the inside of your lungs. And that increases your lung cancer risk dramatically. So you see the ratio is 15 to 1 at 2 picocuries per liter. And I want you to remember that 15 to 1. For smokers, I would like you to remember that the health risk is going to remain 15 times the risk for non-smokers. Now, let's look at this, and you can see, of course, that this is not exactly correct either, but it's 15 to 1 at 2. Now, if it were 15 to 1 at 4, then this number here should be a 30. Notice it's a little less than that, but not much less. At 8, typically the concentration here of 8 would give you for non-smokers a 4. As I pointed out before, half the concentration. And 15 times 4 would be 60. Notice it's a little less than 60. At 10 picocuries per liter, if the non-smoker were 5, that is half the concentration, but we know it's a little less, but let's take it as 5, then 5 times 15 would be 75, and notice it's a little less than that. And it follows along. So I think the way you can remember this entire chart is to remember that for non-smokers, the health risk is about half of the concentration. And for smokers, it's about 15 times what the non-smoker is, what that health risk is. If you bear that in mind, I think you'll find yourself pretty successful in dealing with the questions on the exam, and that's a pretty good way to remember that whole chart to a large degree. You don't remember the numbers precisely correctly, but you get them pretty close. And so the upshot of that chart is this, that non-smoking risks are approximately half the concentration, numerical values, and that's 1 out of 1,000. And that smoking risks are approximately 15 times that of the non-smoker. Now this ends part 3 of the review, and there's a series of questions that follow in after this. So as per the instructions on dealing with the questions, I would like you to now spend some time dealing with the questions that come up on the next page or two, and then return to the video at this part, and we'll begin reviewing part 4.